Photolithography is the process of transferring patterns onto a surface. It's essential in the electronics industry, where micro and nanoscale patterns are fabricated on silicon wafers to create incredibly small, high-performance computer chips. Let's take a look at how a silicon wafer, the substrate, is prepared. A layer of carbon undercoat is applied to the top of the wafer. Spin coating distributes the carbon evenly across the surface. This carbon layer comes into play later in the process. It prevents etching materials from cutting into the wafer base. It also fills any narrow gaps in the underlayers. Next, a layer of silicon hard mask is added. The hard mask protects the underlayers from the etching process, which will dissolve most of the layers above it. A layer of anti-reflectant coating is applied. It minimizes reflections and reduces standing waves. Without the layer of anti-reflectant, light bounces off the bottom layer. This interference causes ridges and defects in the resist. It means the chip won't pass functional parameters. After preparation, the wafer is coated with a thin film of photoresist. Dispense about 1 cc per second of photoresist onto the wafer, spinning at about 1000 RPM. Spin for 30 seconds at the speed necessary to achieve desired film thickness. High-performance chips require very small features. This means using thinner layers of photoresist and smaller wavelengths of light to create them. Higher spin speeds result in thinner layers. DuPont photoresists support the creation of extremely small features. Our ultra-high purity manufacturing process and tight batch control result in high-quality resists that can be spread in very thin layers. DuPont makes custom photoresists optimized for wavelengths from 436 nanometers to the smallest, 13.5 nanometers. As the wafer spins to distribute the photoresist, a thicker bead of material forms at the outer edge. Remove this edge bead with a solvent before the next step. If this buildup is left on the wafer, the excess photoresist will contaminate later steps. Spin for about 15 to 20 seconds at 1500 RPM while spraying with edge bead remover. Cure the coated and cleaned wafer in an oven, typically at 160 to 210 degrees Celsius for 60 seconds. The soft bake step serves to cross-link the anti-reflectant coating polymers, making them impervious to the solvent in the photoresist. It also improves adhesion to the substrate and drives out any residual edge bead removal solvent. Time and temperature for the soft bake step are chosen based on the planned post-exposure bake conditions. Apply top coat using spin coating, just like the previous layers. Dry the top coat with another baking step before exposure. The top coat forms a hydrophobic layer that keeps water droplets off the surface of the wafer. It reduces watermarks and prevents water from penetrating the layers. Top coats are also used to prevent acids from the photoresist from leaching out and contaminating the lens. In immersion lithography, light travels down through lenses and then a pool of water before reaching the photoresist. The resolution of the features is increased by the refractive index of the water, enhancing resolution by 30 to 40%. Current immersion methods can achieve feature sizes below 45 nanometers. Photoresists are light-sensitive materials like the emulsion used in photofilm. In photography, the exposed areas of emulsion darken. In photolithography, the exposed areas of positive photoresist become soluble. They'll be washed away by developer in a later step. Photoresist can be either positive tone or negative tone. With a negative photoresist, the exposed areas become insoluble and remain after the developer solution has passed over them. Place the coated wafer in a scanner, also known as a stepper. A wafer will go through the scanner dozens of times as it builds up the layers of shapes that will become the functional parts of the circuit. Position the chrome reticle, the stencil for the circuit's pattern, over the wafer. The scanner's shutter opens and light shines on the reticle, passing through the clear areas of the reticle and exposing the photoresist. The shutter closes and the wafer stage steps to the next position and repeats the exposure. During the post-exposure bake, a photoreaction happens in the exposed area of modern small wavelength photoresists, such as ARF and KRF. This is a critical step in the process that completes the exposure reaction and makes the photoresist soluble by the developer. Bake for 60 to 90 seconds at 100 to 130 degrees Celsius, depending on the resist used. Post-exposure baking solidifies the remaining photoresist, making a more durable, protective layer in future etching or ion implantation steps. For eyeline photoresist, the post-exposure bake also redistributes the photoactive compound within the film to smooth out any standing waves. For positive tone photoresists, the exposed areas of photoresist are washed away with a developer made of water, surfactants, and TMAH, tetramethyl ammonium hydroxide. Spray TMAH onto the wafer and allow it to sit for up to a minute. Exposed photoresist becomes acidic. Because TMAH is basic, it reacts with and dissolves the exposed areas of resist. Spin off the developer liquid and excess resist particles. Rinse the wafer with deionized water to remove any residue. It is now ready for etching and implantation. Depending on the function and complexity of the chip's design, this process is repeated between 12 and 60 times, building layers of circuits on the same wafer. Each pass uses a different reticle mask to make the next layer of patterns needed for the circuit. In the final steps of production, the chip is diced from the wafer, connected with leads, and packaged.